Good day, everybody. How are you all? Today we are going to talk about chapter 7. So I will share my computer screen with you. So the title of this section is Confidence Interval for a Population Mean Sigma Known. Sigma is the Greek small s. It's a population standard deviation. Whenever we have Greek symbol, it's population characteristic. This one is Greek small s and it's called sigma. It's population standard deviation. Population standard deviation gives an idea about the spread of the distribution. Okay, so mean is in the center and standard deviation is a measure of the spread of the distribution. So in this case, we know the population mean and we also know the population standard deviation. We do not know the population mean, but we know the population standard deviation. Kind of strange thing, but it can happen. We might have a prior estimate of the population standard deviation, but of course, we'd never know the population mean. That's why we are going to construct a confidence interval, which is a range of numbers, starting from a lower bound in the left to a upper bound on the right. So within this range of numbers, the population mean will most probably fall. That is our goal, to construct a range of numbers. And we will assume that we know the population standard deviation. We have described statistical analysis as a four-step process whose steps are formulate questions, collect data needed to answer the questions, describe the data, draw conclusions using appropriate methods. We now discuss the construction of confidence interval, which are one of the most commonly used methods for drawing conclusion. Again, to remind you, suppose I want to find the mean age of all the students at Wilmington University. It's practically impossible for me to reach all the students to ask them what is your age, then add up all the ages and divide by, say there are 10,000 students, divide by 10,000. That's a lot of time because I have to reach all those 10,000 students. Not going to happen practically. Therefore, I work with a simple random sample out of this population of 10,000 students. Suppose my sample size is 50, then I'll ask those 50 students who are randomly selected in the sample, what is your age? I'll have 50 ages, add all those 50 numbers, divide by 50, I get the sample mean age. I'll also have an idea of the sample standard deviation. Okay, from the sample mean age, I'll try to make an estimate of the population mean age. And one of the ways to do that is to calculate or construct a confidence interval. Again, is a range of numbers from a lower bound on the left to an upper bound on the right, within which this range, most probably the population mean will fall. Okay. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to teaching of reading. At the end of the program, the students will be given a standardized reading test. Suppose that the mean score for 100 students in the program was X bar, that is the sample mean, English alphabet sample characteristic. This is X with a line at the top called X bar is the sample mean. It is 67.3. Now administrators want to estimate what mean score would be if the entire population of fourth graders in the district had enrolled in the program. Right now, the best estimate for the population mean mu again is a Greek letter, population mean Greek letter, mu is m in Greek language, small m, is a sample mean. So one single point estimate of the population mean mu is the current X bar sample mean, which is 67.30. This is called a point estimate. So you have the big envelope or the big rectangle of population of all fourth graders. We want to estimate the population mean mu. And we have collected a simple random sample of 100 students and found the sample mean to be 67.30. This is a single point estimate of the population mean age. It is very unlikely that X bar is equal to 67.30 is exactly equal to the population mean. In order for the estimate to be useful, we must describe how close it is likely to be. For example, if we think that it could be off by, say, 10 points, we would estimate mu within the interval or with the interval 57.30 less than mu less than 77.30. So what? Say they thought, let's assume that the sample mean of 67.30 is off from the population mean by 10 points. So the lower end will be 67.30 minus 10. It will be 57.30, and the upper end will be 67.30 plus 10, which is 77.30. This could also be written as 67.30 plus or minus. Plus or minus means two operations written in one step. Minus 67.30 minus 10 gives you 57.30, and 67.30 plus 10 gives you the upper end, 77.30. The plus or minus number is called the margin of error. Okay. The interval used to estimate the value of the parameter is called the confidence interval. So, as I told you before, it's a range of numbers with a lower end and an upper end within which most probably the population mean will fall. In the center, we have the data sample mean, single sample mean, 67.30. We assumed the margin of error to be 10. So the population mean can fall anywhere between 57.30 and 77.30. This interval of number is called the confidence interval. Suppose that we require a certain level of confidence, say 95%, that the interval contains the population mean. The real question, what should be the margin of error be in order to have a 95% confidence that the population mean is in the interval? The margin of error for any level of confidence can be found by using the sampling distribution of X bar. Remember, we can draw many samples of size 50 from the population of students. We will have many values of X bar. Say I have 50 samples, each of size 50. Okay, then I'll have 50 values of X bar. I can divide those 50 values of X bar into a group. Okay, starting with the lowest number. Say the lowest number is 20. So 20 to 25 can be a range. 25 to 30 can be another one. 20 to 25 is the first group. 25 to 30 is the second group. 30 to 35 is the third group. 35 to 40 is the second group. These are all groups of sample mean. So I put all the groups on the horizontal axis of sample mean. And then on top of each group, I draw a vertical rectangle. The height of the rectangle is the relative frequency. That means what proportion of the entire sample of 50. Remember, I have sample of 50 samples. So what proportion of this sample, 50 samples, fall in the first group between 20 and 25. That proportion is the relative frequency, which is the height of the first rectangle. Similarly, there will be a height of the second rectangle, which is between 30 and 35. Okay, so this is a relative frequency histogram of the sample mean. On the vertical axis, we have the relative frequency. On the horizontal axis, we have the sample mean. And this probability distribution is called the sampling distribution of X bar. Okay, we want to construct a confidence interval so that we have 95% confidence in that interval. What does it mean? It means that if we determine the interval from this population interval from 50 samples, I have got 50 values of X bar. So I'll have 50 values of the interval. Sorry, I want to determine the interval 100 times. Let's this time have 100 intervals of size 50. So I have 100 samples of size 50, gives me 100 values of X bar. Okay, from these 100 values of X bar, I can calculate 100 values of the confidence interval with a lower margin and an upper margin, or lower boundary and an upper boundary. Okay, out of those 100 intervals that I've determined from 100 samples of size 50, if I have 95% confidence in my method, 95 of the 100 intervals will contain the actual population mean. That is what is 95% confidence. So the remaining 5 intervals out of 100 intervals that I've determined from 100 samples will not contain the actual population mean. So the 95% confidence measures the effectiveness of the method I have used in determining the interval. Okay. Recalling z-score, recall finding z-scores that bound an area. So that 95% confidence, the blue area is the central area where most probably the population mean will fall. Its area is 0.95. Okay. So what is left in the 2 white tails, unshaded tails, is 1 minus 0.95, which is 0.05. Then because this is a standard normal curve, the center is at 0. Because the normal curve, the standard normal curve is symmetric, the left half is equal to the right half. So the area in the left tail is equal to area in the right tail. Now we know the total area in the 2 tails is 0.05. How do I get that? Because 1 minus 0.95 is 0.05, then that is the area in 2 tails taken together. So area in each tail is 0.05 divided by 2, which is 0.025, which you see as the area of the unshaded area in the left tail and in the right tail. Then we need to find this Z1 value. This Z1 value is sometimes called the critical value. Z2 is also a critical value. Why? Because on the left lies the area in the tail 0.025, where most probably the population mean will not fall. And on the right of Z1, the shaded area where most probably the population mean will fall. Similarly, Z2 is also called a critical value for 95% confidence. Why? Because on the left of it, most probably the population mean will fall. On the right of it, in the right tail, the population mean will most probably not fall. So these are called critical values. How do I find the value of Z1 and Z2? Okay, so in case of Z1, I know the area on the left tail, left of Z2 is 0.025. So I do second, I press the second button on the top left, second button. Then I press the verse button in the third row, verse. This is the verse button, third row, press it. Second verse, and then scroll down or press number 3, which is in norm. Okay, and it asks for an area. The area is the area in the tail, left tail, which is 0.025. The mean, as I said, the center is 0. So do not change it. And the standard deviation for a standard normal curve is 1. Do not change it. Go to paste. Whenever we go to paste, we have to hit the enter button 1 time and then 1 more time. And that critical value of Z1 comes out as minus 1.96. Actually, it comes out as minus 1.9599, which we round to minus 1.96. We could have done the same calculation, similar calculation for Z2, but by symmetry, since the area in the left tail is 0.025 and area in the right tail is 0.025, by symmetry, the Z2 value, since it is on the right of the center, it will be positive, same value, 1.96. Okay. Using tables or technology, okay, that is 95% of the area is bounded within 1.96 standard deviation. The number 1.96 is called the critical value, and I explained why it is called critical value, because it separates the least probable region in the 2 tails from the central area where most probably the population mean will fall. Okay, least probable region from the most probable region, that's why it's called a critical value. In the center, the mean where the peak is the highest in the horizontal axis, Z value is 0, that is the mean. On the left of the mean, Z1 is minus 1.96. On the right of the mean, Z2 is positive 1.96. When the sample size is large, n greater than 30, central limit theorem tells us that the sampling distribution of x bar, which is the probability distribution of x bar, like I explained, is approximately normal with mean mu x bar and standard error. Standard error sigma x bar means the standard deviation of the probability distribution of x bar is sigma x bar. Because the sampling distribution of X bar is normal, 95% of all the sample means will lie within 1.96 standard deviation of the population mean. Okay. So X bar will fall within 95% within, so because the sampling distribution of X bar is normal, 95% of all sample means will fall within 1.96 standard deviation of the population mean. What does it mean? That means X bar will fall between mu minus 1.96 sigma X bar on the left and mu plus 1.96 X bar, sigma X bar on the right. Remember, this is the probability distribution of X bar that you see in the picture. Its center is mu X bar equal to mu. Its standard deviation of this curve is sigma X bar, which is also called standard error. Now, remember, sigma X bar is actually equal to sigma divided by square root of n. So now we are talking about what are the left boundary and what is the right boundary of X bar sample mean. But we are interested in finding a 95% confidence interval for population mean. We do not want 95% confidence interval for X bar. That is not our goal. So we do algebraic manipulation, and finally the confidence interval, 95% confidence interval for the population mean comes out as X, the lower boundary comes out as X bar minus 1.96 sigma X bar. Sigma X bar, remember, is a standard deviation of the sampling distribution, also called standard error, and sigma X bar is equal to sigma population standard deviation divided by square root of the sample size. So the lower boundary of 96 for the 95% confidence, the lower boundary of the population mean is X bar minus 1.96 times sigma X bar, and the upper boundary is X bar plus 1.96 sigma X bar. With 95% confidence, the population mean is contained in X bar plus minus 1.96 times sigma X bar. In other words, the margin of error, remember the plus minus term is the margin of error. So the margin of error is 1.96 times sigma X bar. In general form, margin of error 1.96 is the critical value of Z multiplied by standard error, which is sigma divided by square root of n, where n is the sample size. Okay, for example, on the new approach to reading, suppose that we know from the past results that the scores on the standardized reading test have a population standard deviation sigma equal to 15. So the standard error is sigma X bar is sigma divided by square root of n. My sample size n is 100 as given in the top on the right, the square. So sigma X bar is 15 population standard deviation divided by square root of 100, or 15 divided by 10 is 1.5. So what is the margin of error? It is the critical value multiplied by standard error. So critical value for 95% confidence we showed is 1.96 times standard error is 1.5. So 2.94, that's your margin of error. Hence, the confidence interval for the population mean is between X bar minus 2.94 and X bar plus 2.94. Now we know X bar is 67.30. So on the left boundary is 67.30 minus 2.94, and the right boundary is 67.30 plus 2.94. So with 95% confidence, we can state that the actual population mean will fall between 64.36 and 70.24. That 95% confidence means if we estimate the interval from 100 samples 100 times, 95 of those intervals will contain the actual population mean. Remaining 5 intervals will not contain the population mean. So that 95% confidence level is a measure of the effectiveness of the method that we used to construct the confidence interval. Point estimate is a sample mean is a single number that is used to estimate the value of an unknown parameter. Parameter is a population characteristic or population mean. Confidence interval is an interval that is used to estimate the value of a parameter. The confidence interval is a percentage between 0% and 100% that measures the success rate of the method used to construct the confidence interval. The margin of error is obtained by or computed by multiplying the critical value of z by the standard error. Okay. Find the critical values for confidence interval. Okay. So we can use the table, or I will explain it to you how to do it in the calculator. Okay, suppose we already did for 95%, that means the area in the center is 0.95. So area in the two tails is 0.05, then we divided 0.05 by 2 to get the area in each tail, which is 0.05 divided by 2 is 0.025. And then we went to in-norm function. How about when the confidence level is 90%? Then the area in the center is 0.9. What is left in the two tail is 1 minus 0.9, which is 0.1. That is the area in the two tails combined. Now we want to find the area in each tail. So divide that 0.1 by 2. So area in each tail is 0.05. How to find the critical value on the left? Go to second, then verse on the third row, then select number 3. Now the area on the left tail is half of 0.1, which is 0.05. Mean is still 0, standard deviation is 1, paste, enter, and the value is minus 1.645. On the right, it will be 1.645. So on the left of the mean, the center is 0, left of the mean, critical value is minus 1.645, right of the mean, the critical value is positive 1.645. You can do the other similarly. So they give you the margin of error. We know the critical value of z for 90% is 1.645. So 1.645 multiplied by margin of error multiplied by the standard error, which is 2.3, gives you the margin of error. And then sample mean minus the margin of error and sample mean plus the margin of error are the two boundaries for the 90% confidence interval for the population mean. Okay, sometimes we may need to find critical value for a confidence interval not given in table A.3. To do this, it is useful to learn a notation for a score with a given area to its right. So area in the center is the confidence level C level, and that is equal to 1 minus alpha. What is alpha? Alpha is the level of significance. It is the opposite of level of confidence. So if my confidence level is 0.95, then my alpha is 1 minus 0.95, which is 0.05. Actually, it is the area of the two tails is now 0.05 because the area in the center is 0.95. And then I took that alpha value of 0.05 and divided into two equal parts in the two tails. So 0.05 divided by 2 is 0.025. So area in the left tail is alpha by 2, area in the right tail is alpha by 2. So the critical value of z on the left is called minus z alpha by 2 because the area in the left tail is alpha by 2. And the critical value on the right tail is called z alpha by 2 because area in the right tail is alpha by 2. So basically, each of the z is indicated by area either to the left of it or the area to the right of it. For the left tail, it is minus z alpha by 2. Area to the left is alpha by 2. For the right tail, it is z alpha by 2 because area in the right tail is alpha by 2. Okay. So we will not do all this. We'll just skip this. Sigma is usually not known. The method described for constructing a confidence interval for a population mean requires us to know the population standard deviation. How do we know the population standard deviation? We don't even know the population mean. The advantage beginning with this case is that it allows us to use a familiar normal distribution. In practice, sigma is usually not known, and we will learn how to construct confidence interval in that case in the next section. The assumption for constructing a confidence interval for a population mean when the population standard deviation is known are, we have a simple random sample size is large, n greater than 30, or the population is approximately normal. Find the critical value z alpha by 2 for a 98% confidence interval. Area in the center is 0.98. What is left? So that is 1 minus alpha. So what is alpha? Alpha is 1 minus sea level or 1 minus 0.98 is 0.02. That is the area in two tails is 0.02. Now area in each tail because of symmetry will be divided by 2. So 0.02 divided by 2 is 0.01. That is the area in each tail. Okay. So now let's find out the left critical value. So second verse 3. Area is now on the left tail is 0.01, not 0.02. 0.02 is the total area. Divide that by 2.01. So area in the left tail is 0.01. Mean is 0. Standard deviation is 1. Paste, enter and enter. And that critical value on the left tail is minus 2.326. So on the right tail, the critical value will be positive 2.326. Okay. Says find the margin of error for a 99% confidence interval. So area in the center is 0.99. What is left in the two tail is the alpha value. 1 minus 0.99 is 0.01. Divide that by 2 is 0.005 is the area in each tail. Now do second verse 3. Area in each tail is now 0.005. So plug in 0.005 for the area. Mean is 0. Standard deviation is 1. Paste, enter and enter. The critical value of z minus z alpha by 2 in the left tail is minus 2.576. That's the critical value on the left. The critical value on the right will be positive 2.576. And the standard error is given as 0.4. So margin of error is 2.576 times 0.4, which is 1.0304. The margin of error is always critical value multiplied by standard error. An IQ test was given to a simple random sample of 75 students at a certain college. The sample mean score was 105.2. Sample mean. Score on the N is 75. Score on this test are known to have a population standard deviation of 10. Verify that assumptions are satisfied. Well, the sample size is 75, which is greater than 30. Therefore, we are okay. Okay. So mean score is given as 105.2. Verify, so assumptions are satisfied. Now the construct a 90% confidence interval for the mean. So we need to find out what is the critical value of z for a 90% confidence interval. Area in the center is 0.9. Area in the two tail is 1 minus 0.9 is 0.1, which is the value of alpha. That is the area in two tails is 0.1. Divide that by 2. To get area in each tail. 0.1 divided by 2 is 0.05. Second verse 3. Area is now 0.05. Mean is 0. Standard deviation is 1. Paste, enter and enter. So we get a critical value of 1.645. So 1.645 multiplied by the standard error will give you the margin of error. Now let's find the standard error. Standard error is sigma divided by square root of n. So it is 10 divided by second x square gives me the square root. X square is in the first column halfway down. Second x square give me the square root. Inside the square root sample size is 75. 10 divided by square root of 75 is 1.154. Multiply that by the critical value of z, which is 1.645. So critical value of z multiplied by the standard error gives me the margin of error, which is 1.899, or you can take 1.9. So what will be the lower boundary? It will be the sample mean minus the margin of error. So population mean minus the margin of error. Sample mean minus the margin of error. So sample mean is 105.2. minus the margin of error I calculated as 1.9. The lower boundary is 103.3. And what is the upper boundary? Sample mean plus the margin of error, which is 1.9, is 107.1. So with 90% confidence interval, we can state that the actual population mean will fall between 103.3 and 107.1. Let's go to the step one more time. What did I do? First, I found out that the sample size is 75, which is greater than 30. So therefore, we can proceed with the method. Okay, the assumption is sample size has to be greater than 30. Construct a 90% confidence interval. So first we have to, area in the center is 0.9, that is 1 minus alpha. Alpha is the combined area of two tails, is 1 minus 0.9, 0.1, divide that by 2.05. Then second verse 3, in norm, area in each tail is 0.05. Then mu is 0, sigma is 1, pest, enter and enter. Critical value of z, we'll get the negative value, but we'll use the positive one, is 1.645. That has to be multiplied by the standard error to give you the margin of error. What is standard error? It is population standard deviation 10 divided by square root of 75, which is 1.154. That will be multiplied by the critical value of z, which is 1.645. And that gives us the margin of error as 1.9. Now the sample mean minus the margin of error gives me the lower boundary, which is 103.3, and the upper boundary is the sample mean 105.2 plus the 1.9, 107.1. So with 90% confidence, we can state that the actual population mean will fall between 103.3 and 107.1. Okay, now the part C, is it likely that the population mean is greater than 100? Yes, with 90% confidence, we can state that because the lower boundary is 103.3, which is greater than 100. So yes to part C. Okay. Now, how to do this in the calculator without going through this long procedure? So we will press the stat button. Then we will highlight the test on the top row, stat button, highlight test on the top row, scroll down with the down arrow key to Z interval and hit enter. Okay. Input should be on stats because we know the summary stats for the sample. So input first line should be flashing on stats. Sigma is population standard deviation is 10. X bar is 105.2. N is 75. C level is 0.9, 90% confidence, and we calculate. So stat, test, scroll down to Z interval because we know the population standard deviation. Input is on stats, sigma is 10, X bar sample mean is 105.2, N is 75, C level is 0.9, scroll down to calculate and hit enter. And the answer is same, 103.3 and 107.1. So with 90% confidence, we can state that the actual population mean will fall between 103.3 and 107.1. You can do this on your own. Okay, so that's the end of this part. Okay. So let's go to the other set of slides that I have for you. Other set of slides. Here it is. Okay. Slideshow from the beginning. Okay. The second section is 7.3, which is confidence interval for population proportion. Remember, P is the population proportion. So these are the objectives. Construct a confidence interval for a population proportion. Find the sample size necessary to obtain a confidence interval of a given width. And describe a method for constructing confidence interval. We will not cover section 3 in this. We're not going to do tables, so I'll skip through it. Construct a confidence interval for a population proportion with TI-84 plus. The National Association of Music members, merchants, surveyed 800 parents of children 5 to 18, and 632 of them said that music education has a positive effect on academic performance. So 632 parents out of total of 800 parents. So sample size N is 800. And the success, we are looking for parents who will say, yes, music has a positive effect on academic education, academic performance. 632 of them said so. So my sample proportion is 632 out of 800. Assuming these parents to be a random sample, we would like to construct a confidence interval for the population proportion of parents who believe that music education has a positive effect on academic performance. P is the population proportion of individuals who are in a specified category. In this case, success is parents who think music education has a positive effect on academic performance. X is the number of individuals in the sample who are in that success category, specified category. N is your sample size. N is, of course, larger than X. And P with a thing at the top called P hat is the sample proportion of individuals who are in the specified category. P hat is given as X over N. These are the formula point estimate P hat. This is the sample proportion. This is a single value or point estimate of the population proportion is X over N. Standard error of P hat is given by this. This is the standard deviation of the sampling distribution of P hat and is given by square root P hat times 1 minus P hat divided by N. Remember, the margin of error is the critical value of Z multiplied by standard error. Once we know the margin of error, then we can construct the confidence interval for the population proportion by using P hat plus minus margin of error. Of course, we are not going to use the formula, so I will show you how to use the calculator. The method for constructing a confidence interval for a population proportion requires that the sampling distribution be approximately normal. The following assumptions ensure this. We have a simple random sample. The population is at least 20 times as large as the sample. The items in the populations are divided into two categories. One is success, the other is failure. Remember, in the success is a group of parents who think music has a positive effect on academic performance. So what is the failure? People or parents who do not think music has a positive effect on academic performance. The sample must contain at least 10 individuals in each category. Okay, so one prop Z interval is what we have to use. Okay, so let's do this one. In a survey of 800 parents and 632, out of 800 parents, 632 said that music education has a positive effect on academic performance. Construct a 95% confidence interval for the proportion. This is the population proportion of parents. So we are looking for two numbers, a lower boundary and an upper boundary within which most probably population proportion will fall. And we are looking for a 95% confidence interval. So we begin by checking the assumptions. We have a simple random sample, that's fine. It's reasonable to assume that the population of parents is at least 20 times as large as the sample. My sample size is only 800. So you're thinking population is 20 times, more than 20 times 800. And items in the population can be divided into two categories. Your success is 632 and your failure is 800 minus 632, 168. Who do not think music has a positive effect on academic education. Now notice 632 and 168. 632 is success, 168 is a failure. Both of them are greater than 10. So all of these conditions we needed to satisfy, which we did, so we can move forward. Okay. So we have to construct a 95% confidence interval for the population proportion of parents who think music has a positive effect on academic education. So again, we press the stat button, put the calculator on, press the stat button, then highlight test on the top row, like they said over here. Okay, then we scroll down to one prop Z interval. Not one prop Z interval. So it is not in the first screen. It is, you have to go down with the down arrow key and come to one prop Z interval. Prop stands for proportion, Z interval. Okay. So your success is your X. What is your X? X is 632. What is your N? N is 800. And what is your C level? 0.95. And you go down to calculate and hit enter. So with 95% confidence, we can state. So population proportion will fall between points 76178 and 0.818. Okay, so stat, test, scroll down to 1 prop Z interval, hit enter. Your X is 632, N is 800, your C level is 0.95, and you calculate. And so the 95% confidence is between 0.762 and 0.813. With 95% confidence, we can state that the actual population proportion will be between 0.762 and 0.818. Okay. Excel, we are not interested. Simple random sample of 200 third graders in a large school district was chosen to participate in an after-school program to improve reading skills. After completing the program, the children were tested and 142 of them showed improvement in their reading skills. So number of successes is 142, N is 200. What is failure? 200 minus 142 is 58. So now success is 142, failure is 58. Both of them are greater than 10, so we can use the method. The assumptions are satisfied. And we will do the 95% confidence interval. So stat, test, and we scroll down to 1 prop Z interval and hit enter. X is 142, number of successes. N is total sample size is 200. And we are doing a 95% confidence level, so 0.95, and we calculate. And the 95% confidence interval is between 0.647 and 0.773. So with 95% confidence, we can state that the actual population proportion of students who show improvement is between 0.647 and 0.773. Now notice the lower boundary is 0.647, which is greater than 60% or 0.6. So the part C says, is it reasonable to conclude that more than 60% of the students would improve their reading scores after completing the program? The answer would be yes, because the lower boundary starts from 0.647. Okay. Find the sample size to obtain a confidence interval of a given width. This is the formula. N is equal to P hat times 1 minus P hat multiplied by Z alpha by 2 divided by M in parentheses. The whole thing is squared. What is M? M is your margin of error. That will be provided to you in the problem statement. Sometimes we do not, in order to use the formula P hat times 1 minus P hat times Z alpha by 2 by M squared, we need to find the value of our M, margin of error, and P hat. We can set the value for margin of error, but we don't know ahead of time what P hat is going to be. There are two ways to determine a value of P hat. Use a value to established that is available from a previously known sample, or we can assume P hat equal to 0.5, and then it will be 0.5 multiplied by 0.5, the first two terms. So N is 0.5 times 0.5 times the Z alpha by 2 divided by M. Remember, M is the margin of error which will be given to you, squared. Now 0.5 times 0.5 is 0.25. So in the second formula, N is 0.25 multiplied by Z alpha by 2 divided by margin of error squared. In a previous example, in a sample of 800 parents, 632 believe that music education had a positive effect on academic performance. Estimate the sample size so that a 95% confidence interval will have a margin of error of 0.025. Now for 95%, we know Z alpha by 2 is 1.96. Margin of error is given to us as 0.025. Now P hat is also 632 divided by 800, which is 0.79. So how will I calculate the sample size? Is one shot in the calculator. So first I type in p hat, which is 0.79. 79. Then left parenthesis 1 minus 0.79. Then right parenthesis, then again left parenthesis. Just the way it is written. Z alpha by 2 is 1.96 divided by margin of error, M, is 0.025. Then right parenthesis, okay? And we need to square that thing inside the parenthesis, last parenthesis. So we press the X square button at the end and hit enter. We get 1019.71, which should be rounded to 1020 because we cannot have a fraction, for example. We always round it to the higher number, next higher number. What is the advantage of doing that? That reduces the margin of error, which is good. Plan to estimate 95 proportion of people education. We have no value of p hat. So it will be 0.25 left parenthesis 1.96 for z alpha by 2 divided by margin of error is 0.025 right parenthesis and then square it by pressing the X square in the first column, and the answer is 1537. Okay. So let's do this. In a preliminary study, simple random sample of 100 computer chips were tested. 17 of them were found to be defective. Now another sample will be drawn in order to construct a 95% confidence interval for the proportion of chips that are defective. Remember, for the first sample, it's 17 out of 100. So p hat is 0.17. Use the result of the preliminary study to estimate a sample size needed so that the confidence interval will have a margin of error of 0.06. So p hat is 0.17, left parenthesis 1 minus 0.17, right parenthesis multiplied by z alpha by 2. For 95%, it is 1.96 divided by margin of error is 0.06, right parenthesis, then square the last parenthesis and hit enter. Answer is 151. Okay. A pollster is going to sample a number of voters in a large city and construct a 98% confidence interval. So we need the z alpha by 2 value for that. 98% confidence interval for the proportion who support the incumbent candidate for a mayor. Find the sample size so that the margin of error will be no larger than. So M is 0.05. We do not know p hat. So we will assume p hat is 0.5. But before that, we need the z alpha by 2 for 98% confidence interval. So the area in the center is 0.98, where most probably the population proportion will fall. Area in the two tails is 1 minus 0.98, which I do in the calculator is 0.202. This is alpha value. Area in two tails is 0.02. Now we have to divide by that by 2 in 2 equal parts. So area in each tail is 0.01. To find the z alpha by 2, second verse, then we go to 3 in non. Area in each tail is 0.01. So 0.01, 0 and 1, mu is 0, sigma is 1. Do not change it. Paste, enter and enter. Critical value is 2.326. So we will use that. So first is 0.5 because we do not know p hat. We'll estimate p hat to be 0.5. Then left parenthesis 1 minus 0.5. Okay. Right parenthesis. Then again left parenthesis. Z alpha by 2 is 2.326 divided by margin of error is 0.05. Right parenthesis, and we have to square it by pressing the X square button, and the answer is 542. It cannot be 541.02, cannot cut a person into 0.02, so we will round it to the next higher number. We do not round it down to 541. We round it up 542. Okay, so that is the minimum sample size that is necessary. We will not cover this in this course. So let's go back to stop sharing. Okay. If you have any question, you can always shoot me an email and I'll get back to you as soon as I can. And thanks for watching. And I'm coming back next time with another section of this textbook. Take care. Have a nice day. See you next time.